Yes. Okay, I should be recording now. So, okay. So yeah, I guess a couple of remarks are, so I'm going to be talking about K-theory, as you can see in the title. I'm going to be talking about more specifically topological K-theory. And okay, so so if you took a look at my last talk, either the notes or if you watched it on YouTube or on Discord or something, that's kind of the knowledge, those are the preliminaries which I'm assuming. So I won't be going over any of the stuff about vector bundles. So if you forget any of those definitions, then I guess it might be helpful to just have open some kind of a separate tab with the other talk, just in case there's a definition which you forgot from the last talk. So I'll be assuming the knowledge of what the definition of the K-theory of X is, and what a vector bundle is, and that type of stuff. Okay, so so topological K-theory, that's still quite a broad subject. So what exactly am I going to be talking about? So to introduce, so as I said before, I will be beginning where I left off in my last talk. And so at the end of the talk, if you remember, I defined the Grothendieck group of a monoid, which is basically a method for turning a monoid into a group. And so after we noticed that the isomorphism classes of vector bundles over some space X is a monoid with the Whitney sum, then you can define the K-theory of X by just taking the Grothendieck group of this monoid. So in this talk, I'm going to go a bit deeper. I'm going to give a few related definitions. So the definition of reduced K-theory is something I'm going to go over. Relative K groups, and more, and some other things. And the point of doing this is that I'm going to be looking at a few different interpretations of K-theory. So the first ones I'm going to do are the homotopical interpretation, which and these isomorphisms, which I'm underlining right now, are really important in that. And so after looking at that, and some remarks related to that, I will look at K-theory as a generalized cohomology theory. And I'm gonna go through each of the Eilenberg Steenrod axioms for cohomology, and we're gonna check which ones hold for K-theory using the definitions which I'll give at the time, and which ones don't. Okay, and during both of these sections, I'm going to be looking at Bott periodicity from both of these perspectives. And so I kind of decided to put this in the introduction, halfway through while I was writing this talk. But all spaces are assumed to be compact. Okay. So yeah, first of all, we're going to be looking at the homotopical point of view, and I guess you could say some further definitions. So the first thing we're going to look at is the reduced K-theory. Now, the functor K is contravariant in the category of compact spaces. So if we have a continuous map F between X and Y, then we have an induced map F star between the isomorphism classes of vector bundles over Y to the isomorphism class of vector bundles over X, which is induced by pulling back the vector bundle, basically. And so from this we get another map between K of Y and K of X. So it's contravariant. It's not covariant in the category of compact spaces. So that means that the inclusion from a point P to a space X induces a map alpha between K of X and K of P, which is isomorphic to the integers, because this right here, so vect, the isomorphism classes of vector bundles over a point P, is going to be the natural numbers. So just so each natural number will correspond to the dimension of the trivial bundle of rank n, and then obviously taking the Grothendieck group of the natural numbers will leave us with the integers. And so we can define the kernel of this map alpha to be the reduced K-theory of X. So this is what we mean by the reduced K-theory of X. And another reason why the reduced K-theory of X is very nice is because the map beta, which is the collapsing map, so it takes in X and it's going to collapse it to a point P, which is the inverse of the inclusion of the point into the space itself, is the collapsing map. And the induced map beta star, which goes from the integers to K of X, induces a natural splitting between K of X, the reduced K-theory of X, and the K-theory of a point. And so what we get is that this nice result that the K-theory of X is isomorphic to the reduced K-theory of X plus direct sum with the integers. And okay, that's nice. So okay, first of all, this is good, because if we manage to study the reduced K-theory of X, if we manage to find that a bit easier to study, then indirectly what we're doing is studying the K-theory of X, which is one of the main goals, or if not the main goal, of topological K-theory. Okay, so now we're going to take a slightly different route, but if you just stay with me for a little bit, then you'll see why I'm taking this slightly indirect route. So for every vector bundle E, there's a locally constant function R, and what it does is it takes in a point in X and it outputs the dimension of EX, which you'll recall from last talk is the vector, the dimension of the vector bundle structure on every point X over E. So now if we let H0 of Xn be the monoid of all such constant functions with composition, then there's no reason that, because this is a monoid, there's no reason that we can't look at the Grothendieck group of this, and then look at of both vect X and this monoid here, of the locally constant functions like this, and we can look at the map, induced map R, sorry, we can look at the map which R induces between vect X and this monoid here, and the Grothendieck group of this, the symmetrization of this monoid, becomes the first check cohomology group of X. So this is the locally constant functions with values in the integers, and another way to look at this is that this is actually isomorphic to the homotopy classes of maps between X and the integers. Okay? And so we have a group homomorphism. After all of this, we have a group homomorphism between the Grothendieck group of vect X and this monoid here. And we're going to let K prime of X be the kernel of this map R. And it turns out that this K prime is surprisingly closely related to a lot of things which we've been looking at. So first of all, it's closely related to the reduced K-theory of X in the following way. For compact spaces X, we have a split exact sequence, which looks like this. That is, K of X is isomorphic to K prime of X plus this cohomology group here. If it fits like that. And furthermore, if we have the x's connected, then we have a canonical isomorphism between K prime and the reduced K theory. Sorry, this underline is, yeah, which is important, right? So for example, for the n sphere, these groups are going to coincide. And the proof of this is actually not too difficult if you want to have a go at it, but for the sake of time and more important proofs later, I'm going to just omit the proof now. Okay, so actually it turns out that this is not the only thing that this mysterious group K prime of x is related to. It actually is isomorphic to the direct limit of the isomorphism classes of vector bundles of rank n over x. But in order to show this isomorphism, first we're going to need a theorem, which we're going to rely on heavily to show that the isomorphism, which we'll define later, is in fact an isomorphism. Okay, so if we denote by theta n the trivial bundle of rank n over x, then every single element of the K theory of x is of the form the class of E minus the class of theta n, the trivial bundle of rank n, for some n and for some vector bundle E over x. Furthermore, we have that these two elements are equal to each other if and only if there's an integer p such that E Whitney sum with the trivial bundle of rank m plus p is isomorphic to F Whitney sum with the trivial bundle of rank n plus p. Okay, so this proof again is somewhat technical, and the theorem itself is quite important for the next couple of slides, but I didn't include it for because it is quite a technical proof. I mean, you can have a go. It's not crazily hard, but but I didn't want to include it in this talk because that's not really the point of this talk. Alright, so if we go on to the... Okay. Okay, so next next thing we're going to do is we're going to study the direct limit of all of these the isomorphism classes of vector bundles of rank n over x. Okay, so again, like I said before, we want to show this isomorphism highlighted here, right? We want to show this, and somehow we're meant to use this theorem to do so. So okay, we can put an abelian. So okay, so first of all, I might as well justify the word isomorphism here, because we haven't yet put an abelian monoid structure on this direct limit here. But we can do so via the Whitney sum, like this. Oh, whoops, that's a terrible underline, but you know what I mean. Okay, and so if we write E dot for the class of E in this isomorphism classes of vector bundles of rank n over x, if we write the class of this in that monoid, we can see that the class of E minus the class of the trivial bundle of rank n is in the kernel of this map R, which we had before. And so the correspondence where we put E to this right here induces a monoid homomorphism between the direct limit of all of these vector n's and K prime, which is K prime of x, which is the kernel of this map. Okay, so we need to show that this is an isomorphism, which is okay. All right, so let's show that it's injective first. We need to show injectivity and surjectivity. So by our preliminary theorem up here, up here, we have that two classes like this elements of this are equal if and only if this we have an isomorphism which looks like this, right? And so because of this, our map is injective. So because this is an if and only if statement, this is sufficient for injectivity. And now we have to show using this. We have to show that this is that the map is surjective. So if we let X be in this group K prime, then again we can use this preliminary lemma to say that X is of this form, where the dimension, so where R of where all this is saying right here is that the dimension of EX is equal to n for all x. And so we have this phi, this map which we got here, is surjective. And so we've shown injectivity, we've shown surjectivity, and so it's an isomorphism. And so what we've shown is that this group, the kernel of this map here is isomorphic to the direct limit of these monoids right here, which is really good. But you might be wondering why this is such a big deal, right? So okay, sure, we showed this cool isomorphism. We kind of used this funky group which is related to this K prime of X under certain conditions. Big hoot. But why? Why did we take this detour to do this? Well, turns out, if we scroll down, that we have the following isomorphisms between the isomorphism classes of real vector bundles of rank n over X, and this is isomorphic to the homotopy classes of maps between X and the classifying space of the nth orthogonal group. And similarly, you have this isomorphism here for the complex vector bundle version. And now we're starting to see, so if we go right up to the top again, we're getting these BOs, these BUs, we're getting quite close to showing this isomorphism here. The question, and if I didn't rub it out, yeah, and look, the integers are coming in here. We're getting splittings, so if we rewrite this as K prime of X plus the homotopy classes of maps between X and the integers, that's where the integers part is coming from, right? So the real thing we have to do here is just combine all of this information which we've gathered, and suddenly we're getting a point of view of K-theory which could be helpful for homotopy theory, right? So if you would like, because this is quite an important theorem, if you'd like to, I don't know, afterwards, if you'd like to prove it, then by all means do. But I'm gonna, instead, I'm gonna use this to prove something else, and that is this. If we let BO be the direct limit of these classifying spaces of orthogonal groups, and similarly BU being the direct limit of these classifying spaces of the unitary groups, then we have natural isomorphisms between K prime of X of these real vector bundles, like so, and similarly like this. And now we're starting to get really close. We're starting to get really close to the theorem we wanted to prove this whole time for the homotopy theory part of this talk. But we just need a few more details to make this fully concrete. We just need a couple more details, but we're really close. And suddenly we're going from, well, okay, why did we are we just doing this for kicks and for some, for some fun? We're just taking a quick detour because we're getting stuck. To all of a sudden, this theorem appears, and suddenly we're really close to getting our final homotopical point of view. Okay, so let's actually prove this theorem. First of all, note that we can interchange these direct limits with the homotopy classes of maps between X and the classifying space of the orthogonal group, which if you would like, you can check. I don't think you can do this in general, but I think that because X is compact and because of certain properties of these orthogonal groups here and their classifying spaces, we are allowed to do this. And furthermore, recall that we have this isomorphism from just before. Now note that the map between the isomorphism classes of real vector bundles over X of rank n to the isomorphism classes of real bundles of rank n plus 1 over X, which are induced by adding the trivial bundle of rank 1, coincides with this inclusion right here. And so overall, we have this following chain of isomorphisms. K prime of X, so this is isomorphic to this direct limit from before, and this is isomorphic to this direct limit from this. From this, and this because of this statement right here. We're using it again, and this is exactly what we required. And the complex case is analogous, but we just fill in all the details using BU instead of BO. Now, after doing all of this groundwork, after introducing all these definitions, all of these theorems, we finally managed to hit the homotopical point of K-theory, which I was hyping up in the introduction. That is, we have the following isomorphisms. The real K-theory of X is isomorphic to the set of homotopy classes of X, between X and the integers cross the direct limit of these classifying spaces of orthogonal groups. And similarly, we have this isomorphism for complex K-theory. And this is really neat. Immediately note that when X equals Sn, we're suddenly getting fundamental groups of some stuff here, right? Because that's how we define fundamental groups. And so we're already starting to see, okay, we haven't filled in the homotopy theoretical details yet. That's what I'm about to do. But we're already starting to see some kind of applications nearing, some kind of relations at least, maybe not applications, but at least some relations nearing. In fact, we've already got a relation, we've already got this relation right here, but to the homotopy groups. We're getting quite close, right? So let's proceed. Oh yeah, of course, I actually have to prove this, right? So recall from before that we have this splitting here. And because we can write this like that, this is also isomorphic to K prime X plus the set of homotopy classes of maps between X and the integers. For complex K theory, this splitting is, as you can see here, from this theorem, no, whoops, wrong theorem. From this theorem right here, if, okay, this arrow is not going to do it, but from this right here, we can replace this with that, and just stick a C there, and, and this goes back here. And by simple properties of product maps, so like a map between like this induces two maps, the factor onto the first projection and the map onto the second projection. Right, so we can package all of this information right here. We can package it into one homotopy group. Similarly, the case is for real K-theory. If we stuck an R here, then this right here gets replaced there. This right here gets put back there. And again, with this reasoning right here, we can package both of them in like this. And that's exactly what we required. Now, what I'm going to do to wrap up this section, so after this exciting journey, this kind of mush between K-theory and homotopy theory, what I'm going to do is I'm going to finish this section by looking at Bott periodicity, but I'm going to specifically make it from the homotopy theoretical point of view. There's a different version of it which we'll look at later, which is that the negative ith K-theory of X, and we're talking about complex K-theory here, is periodic like this, negative I minus 2 of X, like this. We have this periodicity for complex K-theory, which we're going to look at later. Right now we don't have these definitions, but we can still look at a version of Bott periodicity. We can still have a version of Bott periodicity for but a homotopy theoretical version, not this kind of cohomological mush with K-theory, that type of version, not that yet. Although we will do that soon. Alright, let's see. Okay. What we have is that this right here, this thing, okay, let's get rid of some of these annotations. Alright, this right here, it's eightfold periodic. So X, sorry, no, not this, sorry. This, let me just erase this. Yeah, this right here, this is the eightfold periodic one, which means that it's that BO crossed with the integers is homotopy equivalent to the 8th loop space of BO cross the integers. And this implies that if we write this as the direct limit of all of these orthogonal groups, this is what O is, then if you fiddle around with this a little bit, you will in fact get this homotopy equivalence too. And similarly, the complex K-theory, or at least this part right here, this is twofold periodic. Twofold periodic, right? So its second loop space is homotopy equivalent to the integers crossed with the direct limit of these classifying spaces. And so again, if you fiddle around a little bit, you will get that writing this for the direct limit of the unitary groups, we get that this is homotopy equivalent to the second loop space of this direct limit. Now there's more. We have further implications from this. Oh, okay, maybe not directly from this, but from this we get that the homotopy groups of the infinite orthogonal group are eightfold periodic. So we have eightfold periodic homotopy groups. I'm actually just going to write pi n because I'm not going to have space to write that. So eightfold periodic pi n's homotopy groups. And this has, and the reason for this is if we just take pi n on both sides, we're going to get pi n of u is isomorphic to pi 2n. Sorry, let me write this down here where I have space. So from this right here, we get that pi n of u is isomorphic to this pi n plus 2 of u, because that's just how loop spaces work, really. Yeah. And similarly for this, we get that, if we draw an arrow here, we get that the nth homotopy group of the infinite orthogonal group is isomorphic to the n plus 8th infinite orthogonal group. Okay, so these homotopy groups have been explicitly computed, and they look like this. For the infinite orthogonal group, we have that the 0th homotopy group is the integers mod 2. The fundamental group, as Tetra probably knows from somewhere, are the integers mod 2. The second homotopy group of the infinite orthogonal group is trivial. The third homotopy group of the infinite orthogonal group is precisely the integers. The fourth one is trivial, the fifth one is trivial, the sixth one is trivial, and the seventh one is the integers. And by doing this, we've computed all of the homotopy groups of the infinite orthogonal group. Because if we say, okay, well, Gregor, you're capping, what's the 8th homotopy group of infinite orthogonal group? Well, then I'll say, no, I'm not capping. Look, remember this isomorphism? This is precisely that, because 8 is equal to 0 plus 8, if I recall correctly. Now, similarly for this, we have much less complicated homotopy groups, but it's still worth mentioning. The ith homotopy group of the infinite unitary group is trivial for I even, but then when I is odd, we have that they're isomorphic to the integers. Okay, so that was the homotopy theory section of the talk. So let's just recap what we've done. I'm just going to scroll straight through. So if we look at it from the introduction, we used a bunch of different tools to show finally this isomorphism here, right? So that's what we were doing basically. That's all we were trying to do with this. That's the only time you're going to see this K prime. In fact, I think the only Max Karoubi's text that I know of uses this K prime group here. I mean, I don't think you'll see it elsewhere, really. The whole point of introducing this group was so that we could have a nice, concise proof. If we just lay down all of this groundwork, eventually the proof of this became really simple, right? Because we'd come up with so many different isomorphisms involving, let's say, reduced K-theory. We had some isomorphisms including this K prime of X group. We had some stuff to do with these vector bundles of rank n and their direct limit. And I guess, as you start developing things which are really closely related to this, then eventually you're gonna break through, and you're gonna find the concise, nice theorem that you want, right? We've developed a lot of the theory surrounding this, and eventually we managed to put it all together and piece it all together. Okay. So now let's see if we can do something similar with the cohomological point of view. So K-theory with a little bit more work, right? So we did a lot of different type of groundwork from before, right? We developed some more homotopy theoretical tools. So we looked at this type of thing, right? We looked at some objects surrounding this, but this next part is going to have a slightly different flavor. We're going to be looking at K of X as the 0th homotopy group of X, right? Sorry, not homotopy group, the 0th K-theory group, the 0th K group of X. And what we're going to do is we're going to try and define Kn of X. We're going to try and define K of XY. All of these spaces are compact, by the way. The definition should still be the same for non-compact spaces, but compact spaces are sufficiently nice, basically. We want to define these nth relative homotopy groups. You know, we want reduced. You know, for cohomology theories, we normally have the reduced version, so that would be the reduced K-theory of X. We want to define all of this good stuff, right? And notice here that in these arrows, these 4 things that we want to define, that that this K prime, if we, I don't know if I can draw in it. Okay, I have different colors. This K prime, this is an outsider. Like, it's only here for homotopy theory. Over here, it's happy, but it's not very related to this, to the cohomology theories which we want to develop now. So, let's do this. And I should note that it's not actually going to be a cohomology theory. It's going to be a generalized cohomology theory. Okay, so this is what it's going to be. So let's see why. First of all, we're going to need a big chunky definition. So first of all, denote by X plus the disjoint union of a space X with a point. And actually note that by a splitting that we had really early on, that K of X is precisely the reduced K-theory of X with this point attached. Okay, so what we're going to do is we're going to define negative. First of all, this is the first thing we're going to do. We're going to define negative K groups first. And we're going to use these to define the positive versions. Okay, so, alright, let's see what we got here. We have that the minus nth reduced K-theory of X is just equal to the reduced K-theory of the suspension of X. And this right here is the category of compact spaces with base point attached. Point attached. Okay. Now, the relative K groups here, these are going to be defined as the minus nth reduced K theory, as we have defined it here, of X mod Y. Okay, let's just pause here for a second. This right here smells like excision. The excision axiom. That's what it smells like. I'm just going to point that out now. And this, sorry, this negative n shouldn't be here. This is just like this. And this is the reduced K-theory group of the nth suspension of X mod Y. And these are pairs of pairs of compact spaces. Okay, and now the negative nth K-theory group of X is going to be defined as as the group, the negative nth relative k-theory group of X and the empty set. And so what this is going to be is, this also smells like some other axiom, but I forget what the axiom is called that requires this. I don't have a text on me which I can reference for this, but some other axiom. Let's call it that. Okay, and this is the reduced k-theory, again by definition. This is the reduced k-theory group of the nth suspension of X mod the empty set, and this is just going to be this right here. Let's do this. If you remember, this is just the reduced k-theory of the nth suspension of X with a disjoint base point attached. X is required to be compact. Okay, good. So we got these definitions out of the way. But why? Okay, we got these definitions out of the way. That's good. That's good. We have Bott periodicity again, but this time it's from the cohomological point of view. So this time it's from the cohomological point of view, because before what we were looking at was it from the homotopical, the homopod. That sounds quite cool, homopod. So this is what we're going to be looking at in this right here. Okay, what is Bott periodicity? Well, it's saying that for complex K-theory is twofold periodic, just like with before, but it's said in a slightly different way. And similarly, real K-theory is, well, you guessed it if you were here a few minutes, 20 minutes ago or something. You'll expect it to be eightfold periodic. Okay, so from the version of Bott periodicity before, we can actually prove this quite simply, because we have the suspension loop space adjunction, which is going to come to our advantage here. So I'm going to give the proof for I equals 0. So that is that K of X, the complex K theory of X, is isomorphic to the negative tooth one. I'm guessing that from this you could probably induct. You could probably just use induction to kill the proof. It should be pretty straightforward. Right. So again, recall the definition like this, and reduce this right here means that they're preserving base points. Preserve base points. Okay, so this is what this dash means. Now we have the minus tooth reduced K theory. Sorry, I should probably say minus second. Reduced complex K theory is isomorphic to the set of based homotopy classes of maps between the second suspension of X and the integers crossed with this direct limit of unitary groups. And then we're going to use this step right here. This is important to justify, because otherwise, if I didn't justify this, then the whole proof would collapse. This right here. What's this step doing? This is a sneaky little step, which we can use by what's it called? Suspension. Oh god, that went wonky really quickly. The suspension loop space adjunction. Okay, so this is the justification for this one. And now, this is perfect. The reason that we've swapped it around like this is, we know exactly that this right here from before, so our homotopy one, he's saying hello again. Because this right here is homotopy equivalent to the integers crossed with this BU. Right? That's good. Good. And so now we can replace this with this. And now that's precisely the reduced K-theory, the reduced complex K-theory of X. This is note that this is not the note that this is not the what's it called? Normal complex K-theory, because these are based homotopy classes. So it's reduced, it's not normal. This is preserving base points this time. And again, the real case will be analogous. You just use the 8th suspension and put in the 8th loop space. And use Bott periodicity from before. That's very good. Now we can compute some K groups of spheres, which is always nice. And that's good. So we have that the 0th K group, the 0th reduced complex K group of the 2K sphere is isomorphic to the integers, and the -1th reduced complex K group of the 2 sphere is trivial. And so if we just direct sum with the integers from our splitting at the start, what did I tell you at the start? If we study the reduced K groups, by the splitting we had at the very start, we're indirectly studying these K groups. And so these two results right here, if you just do a big direct sum with the integers, you're going to get just the normal K groups of spheres. Piece of cake. Good. So now, okay, how can we show this? This is going to have something to do with fundamental groups. I mean, you can, if you're not smelling fundamental groups with these these spheres inside these K groups, you know, then I don't know, maybe I don't know what's going on there. So I'm going to give the proof for this one. Again, I'm just going to give the proof for this one. This is immediately going to give us the proof of that one, and the proof for 0 is the same thing. So if you want to fill it in, then you can fill it in, but okay, it's the same thing. Okay, let's see. We have that sorry. The -1th reduced complex K group of the 2K sphere is isomorphic to, well, the reason we have this right here is because the suspension of the 2K sphere is isomorphic to the 2K plus 1 sphere. Because when we do the smash product, if you've listened to the smash product song, we will get this. And again, by definition, we have this part right here. And this, because they're based maps right here, we get this is precisely the 2K plus 1 homotopy group of this classifying space. And then we can get rid of this if we just make this a 2. Or in other words, like this, which we computed before. So that's precisely the form like before. If we go up, where did we do it? Oh yeah, we did it here. So recall that for even I, that is of the form 2 times n plus 1, that is even, it's going to be trivial, right? So therefore, we have that this here is trivial, and so immediately from this right here, we get this equal to the trivial group, and so therefore we have that the -1th complex K group of the 2-sphere. Sorry, I mean not the 2-sphere, the 2K sphere. Like this is isomorphic to the trivial group plus the integers, which is just the integers. Okay, good. So now we can define these things here, these relative groups, like so. And because of Bott period, and by the way, all of our K groups now are going to be assumed to be complex. So from now on, okay, I might as well write this down. From now on, our K theory our K theory is complex. Okay? So you can do all of the analogous definitions and so forth with real K theory, but complex K theory just becomes simpler because it's only twofold periodic rather than eightfold. So, okay, we may define the nth relative K group of X, Y for compact spaces. So these guys are compact pairs to be the n minus 2th one, right? So, okay, hold on, wait a sec. Where do we start? Well, we're going to start with n equals 1, right? Because we've already defined, we've already defined k minus 1 of xy. So when n equals 1, we get that k1 is equal to k minus 1. And so we get k1, and so we have k3, and so forth and so forth. So it does all work out. And similarly for k0, the 0th relative one, we can just do that's just precisely the negative 2th one. Okay, so it's been a long journey. And so we're going to see, to finish off this talk, we're going to see which of the Eilenberg Steenrod axioms for cohomology hold for K theory. Let's see which ones hold, because spoiler alert, not all of them will do. So first of all, the correspondence, which looks like this, is definitely a functor between the pairs of the pairs of compact spaces, the category of pairs of compact spaces to the abelian groups, right? Oh god, the pen is going crazy. Oh my, erase. So this is true, right? That's pretty obvious. Okay. Let's check part 2. We do have, okay, and so the reason you're not seeing anything is because I'm still uncomfortable with using ticks in Beamer, and so I'm just going to draw in the exact sequence containing 6 terms. So on the top, we're going to have the 0th relative K group like this, and then this is going to map to K of X via the again, it's the map induced by the inclusion. Then this is going to map to Y, again induced by the inclusion because because you might be thinking, well, shouldn't the inclusion be going this way? But remember that K theory is a contravariant functor, so it shouldn't actually be going this way. Okay, and then we go down via some connecting and this is all 0, and this goes down. No, I'm writing zeta. How do I forgot how to draw a delta. Delta, there we go. To the first thing, so like this, and then we're going to go to K of X. Sorry, the first one. Like this, and then we're going to go over here like this, and then we're going to go back up like this, and this is an exact sequence containing 6 terms, and it's going to look like this. And now actually you'll be surprised how I think if you check Attire's book, which there's a there's a PDF online. I think there's even a couple of PDFs online which you can easily find of Atiyah's text on K-theory. His proof of this, or something analogous to this, I forget, is pages long. So definitely not a proof for this talk. But in the end, it does turn out to hold. So that's good. And it is a natural exact sequence. All right. So remember when I think I still have the annotation. Oh god, I've gone too far, haven't I? Yeah, smells like excision. That's the first thing I said. I mean, I didn't plan to say that. I just kind of thought, wait a sec, that smells like excision, right? Well, this basically, because remember that excision is one of the axioms for Eilenberg Steenrod axioms, and yes, it does turn out that this is true because that's the definition. Okay, good. Okay, let's see. We press on now. The dimension axiom is the one that fails. So this is stopping us. The reason I'm sad is it's stops K-theory from being a cohomology theory. Because we have remember at the start that I said that the K-theory of a point is isomorphic to the integers, and that's definitely not trivial. So the dimension axiom does fail, but if it's of any consolation, if you're dismayed by this piece of news, if it's of any consolation, then the odd ones, they do follow the dimension axiom. So, I mean, I know that it's devastating to hear that this is true, but hopefully you can take some consolation in the fact that the first K group of a point is trivial. Okay, so let's keep checking. Let's hope that none of the other ones fail. So what we're gonna show here is that homotopic maps continuous. F0 and F1 between x and y induce the same homomorphism between k0 of y and k0 of x. I won't do it for k1, but if you'd like to, you can do so yourself. Okay, so if we let f0 and f1 be continuous maps between x and y that are homotopic, then they induce the same homomorphism between the isomorphism classes of vector bundles over y and the isomorphism class of vector bundles over x. And the proof is omitted of this. But I shall proceed with the proof that I was originally doing, because they induce the same homomorphism between the Grothendieck groups. So, right, if we just, if we have, I actually like this pink, so I'm going to keep going with it. But if we have the same map here, if we have the same map like this, then the map which the Grothendieck group induces, so the k of the vector y, like this. They're gonna induce the same one, right? That's what I'm trying to say. So, uneloquently, the opposite of eloquently, basically. And so we have all of them. So this one, okay, let's go back and tick them. Tick, cross, tick, 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 tick. Okay, good. So we have 4 out of 5 which is not bad. So overall, sorry, let me just rub this out because this wasn't a great expression anyway. So overall, what do we have? We're left with a generalized cohomology theory. Yay! Which is I guess that's good, but then again it's not a cohomology theory. It's kind of sad, but whatever. So that's good. We have a generalized cohomology theory, and the reason it's not just a normal cohomology theory is that the dimension axiom fails. Okay, and also it's twofold periodic, and I'm talking about complex K theory here. Twofold periodic. I mean, Bott periodicity is one of the most. I mean, I think that was I'm at the end of the talk now, so I guess I can ramble on for a little bit about how cool Bott periodicity is. But it was one of these. It was one of like the first. It was not one of the first. It was one of the most fundamental theorems in algebraic topology. I mean, it was really cool. I mean, I think there was there was some kind of quote from Atiyah saying how the paper when Bott first introduced his periodicity theorem, how great and far-reaching it was, and how great that paper was, and so forth. And I mean, I do agree. I mean, it's really cool. I mean, I think the original proof used Morse theory, but now there's some other version. There's some other proofs. There's a lot of different proofs. I think now. I think I don't remember exactly the chain of homotopy equivalences you show, but you show a bunch of them right here. So you have the integers. Oh god, that's a terribly long. You have the integers crossed with BU is homotopy equivalent to some kind of loop space here, and then I think it's the loop space of BU maybe, and then this is homotopy equivalent or to the second one like this. But again, I don't remember exactly, but it's a long chain of these homotopy equivalences, which I find cool. And of course, we had that application that the homotopy theory, the homotopy groups of the infinite orthogonal group and the infinite unitary group, we had that they're eightfold and twofold periodic respectively. We get that the real and complex K theory are eightfold and twofold periodic respectively, and more. So let's read what I wrote for the conclusion. So yeah, okay, we showed that complex K theory is a generalized cohomology theory. So as I said before, roughly what this means is that it satisfies some of the Eilenberg Steenrod axioms. Furthermore, it's periodic for the two. So yeah, twofold periodic. I don't know if this is the correct way to phrase it, but you know what I mean. And next time, so I'm hoping that next time will be during the Easter holidays. So then these next 2 weeks, or however many weeks, we get someone else doing talks, hopefully recording them for my channel. And then when I do my next talk on K theory, we're going to look at some methods for computing these groups. So this was more of an overview of the different ways you can look at them. But next time we're going to be properly computing them. And at some point, I don't know how far away this is from the future, but at some point we're going to look at some applications of topological K theory in other fields of maths. And yeah, that's basically the talk. I think I went slightly over an hour. I'm just gonna stop recording on YouTube. But I'll stay in the VC for a little bit in case there were any comments or whatever. So let me just stop recording.